Hello and welcome. I am Pravir, and today I'll provide a high level introduction to quantum. So, to begin with, I'll start with the idea of what is quantum physics. So, quantum physics is the science that studies the tiniest things in the universe, things like atoms and even subatomic particles like electrons, photons, and even categories of particles like the boson and Higgs boson and leptons and so on. So, imagine shrinking down to the size of an atom. The world would be very, very different at that level. And things wouldn't act like they do in the normal world, if you will. And so quantum physics is concerned with the dynamics and the behaviors that's happening at this atomic and subatomic level. Now, we already have some devices that have been around for many years that operate based on quantum physics, and some common examples are that of the laser and the GPS. And I want to go into the mechanics very simply of how these operate. So there's something called quantization. So here's a vending machine, and we have specific coins that can operate the vending machine. So in this example, there's a 1 cent, 10 cent, 25 that can operate this machine. And these can be thought of as quanta, so they're discrete energy levels, if you will, that can operate this quantization vending machine. So imagine that the output of this vending machine is a ray of light. And you've got a stack of coins, say many 1 cents, many 10 cents, and you keep repeatedly, you put in a 1, then a 10, then a 1, then a 10. And so every time it switches from 10 to 1, this vending machine is going to output a ray of light. And that's basically the basis of how a laser operates. And this flipping between states is instrumental to how GPS operates because you've got a precise timing as this vending machine switches from a state of 1 to a state of 10, back to a state of 1 to a state of 10. And this timing becomes like a clock that's fundamental to GPS. But quantization also has a much wider applicability. So here's a depiction of an atom, and you've got the nucleus in the center, and then you've got electrons that orbit around it. But these electrons can exist in quantized states. So at certain precise levels or create certain precise orbitals around the atom. And these orbitals then become the basis of bonding with other atoms. So all of chemistry is enabled by this quantization, and then therefore all of life is enabled by quantization as well. Here's another important concept in quantum physics. So this is that of wave particle duality of any quantum object. Here we've got a source of light, and it's emitting photons that are particles. It's going through two slits, and it's showing up as an interference pattern at the back on a screen. So it's a wave depiction. And so you've got light that's showing itself both as particles and waves. And this gets us into the idea of quantum awareness. And here's a well-known metaphor. So you've got this entity, Schrodinger's cat, which I've modified slightly because this cat can be either purple color or white color at the same time. And imagine you've got this cat in a quantum box, and while it's there, it can be both purple and white at the same time. But then when you open the box, it becomes either white or purple. So this gets us into the idea of quantum weirdness. And just to illustrate that, if we think about the classical and the quantum worlds, and take two examples. So one is of throwing a ball, and the second is of a car. In the classical world, we know that the ball has a precise path and the car appears stationary. But in the quantum worlds, if you throw a ball, then it's going to be in many different paths or superposed. And similarly, the car is going to appear in many different states or in superposed realities at the same time. And this gets us into this idea of superposition, which is what particles can do in the quantum world. So imagine you've got a spinning coin, and it's got a heads on one side and a tails on one side. In the classical world, when you spin it, it kind of rotates really quick, and then you can say that it's in both states at the same time. But then when it stops rotating, it falls either as a heads or tails. And so this notion of being heads and tails at the same time is what superposition really is. You've got another phenomena called entanglement, and this is when you bring two particles in proximity and you entangle them, then they begin to share quantum properties. And then when you change the quantum property of one, the other one will change instantaneously, no matter how far apart it is. And here, this is just depicted by this quantum dice, as one shows four, the other shows a related four. Then you've got this phenomenon of quantum tunneling, where you've got particles that can tunnel through barriers, just like how ghosts walk through walls. So you've got these what's called quantum weirdness being defined by things like superposition and entanglement and tunneling. And I want to summarize those with by stepping back and considering the story of two hikers. So they frequent some trails in the hills, and they basically have been going there every weekend for many months. And one day, as they're walking along the trail, one of them notices a flash in the corner of their eye, and they kind of get drawn to it. And they walk towards it, and they see it's an opening into a cave. Now, they'd never noticed that cave before, but they step in, and it's a quantum cave. And basically, it has many pebbles and stones in it. And they realize that when they step on a pebble, then it other pebbles in the cave light up. So they clearly must be entangled. And then there's also some water trickling down on the sides of the caves. And this water is creating different kind of patterns. And all of a sudden, they it looks like to them that there are 1,000 different caves. And everything appears very confused. They get stuck in a quantum puzzle. And then one of them remembers that they've got to, in this quantum world, they've got to observe. And as they observe, all the millions of different stones begin to, that are in superposed state due to this rippling water, begin to collapse. The water begins to collapse. The many entrances or exits of the cave begin to collapse. And they're able to then see through observation the one exit that they had entered through and find their way out again. But this is kind of a metaphor also for how quantum computers operate. And imagine that you have to find a special book in a huge library. So if you use a regular computer, you'd be checking books one at a time. It would take perhaps a long time to find that book. But with entanglement and superposition and interference that we began to get a sense of with the rippling water, there's many books that can be checked at the same time. And so they're able to find this special book much more quickly. Another way to depict this is that you've got all these books that have some kind of probability amplitude, and together they define a state of quantum superposition. And then you've got this quantum superposition that passes through an oracle of kinds. So it's some quantum operation. So perhaps quantum gates and specific arrangement of qubits that I'll talk about in a minute. And this oracle flips the probability amplitude of what the book that it recognizes as a special book, and then it runs some interference patterns to increase that, and that's basically how this quantum computer gets to the right answer. So in quantum computers, what's fundamental is qubits. And these are different from bits. So normal computers have bits, and these can be thought of as tiny switches that can be either 0 or 1. Now, quantum computers use qubits, which can be both 0 and 1 at the same time, and that's due to superposition. So when we hear of all these different companies that are quantum companies, quantum computing companies, really what they're doing is that these companies are creating different kinds of qubits. So there's many different qubits on the market. And here's just some examples. You got a photon qubit, you got a trapped ion qubit, amongst many, many different qubits. And some of the applications of these quantum computers is that they can make some new, they're imagined, or they'll begin to make new medicines, they'll create much better batteries and even much cooler video games. But the challenge is that these qubits are super sensitive because of all kinds of quantum noise. And it's like balancing a pencil on its tip. So let's just summarize where we've been so far. So we started off with what is quantum physics? We looked at some present day applications, specifically laser and GPS. We considered how quantization is fundamental to them, and also quantization is fundamental to chemistry and life. We looked at dual wave particle of any quantum object, and specifically of light. We entered into this notion of quantum weirdness, illustrated it through throwing a ball and a car in the classical and quantum worlds. Then we looked at specifically some quantum phenomena like superposition, entanglement, tunneling. We heard the story of the hikers who went to the quantum cave and experienced a lot of these different quantum phenomena. We saw quickly how a quantum computer operates, how it gets to the right answer, how it's comprised of qubits, ways to create qubits that really drive the different companies that exist. And then we considered at a very high level the kinds of applications that could result. And to summarize, if we think about quantum physics, we could say that it's a journey into a tiny world. And quantum computing is like the creation of a new kind of supercomputer that we call a quantum computer. And it operates through these quantum phenomena like entanglement, superposition, interference, and so on. Now, as we look to the future, what's going to be more and more important is the combination of applying quantum computing, quantum technology, things like quantization and AI. And that's going to lead to discoveries at the quantum level and to us being able to see and understand the world completely differently. And that's going to lead to a whole bunch of different technologies and applications. And that's really what's in store for us going forward. So with that, let me wrap it up. Thank you.